Okay, so today we're going to talk about Debaune's problem. He was I think he was a Dutch geometer at the time of Descartes, and he actually wrote Descartes a letter in autumn of 1638. And he basically asked the following problem. So he wanted to find a curve, y is f of x, such that at any point on the curve x naught and y naught is equal to f of x naught, the tangent line to the curve at that point, we'll just call it t sub x naught of x, satisfies t of x naught, the tangent line, at 1 before the point of tangency is 0. So what does this look like? Well, you have your y-axis, x-axis, and you have a curve like that. So you have your x naught, y naught here. Say that's tangent line, so this would be x naught. The point where the tangent line crosses the x-axis would be x naught minus 1. So this would be y f of x, and this is t of x naught of x. So that was the general problem. He didn't use these words, he used slightly different phrasing, noting the fact that you have a triangle here, so it would satisfy certain trigonometric properties. So we're going to solve this problem. And the first step is to reword it. So we know tangent line looks like y naught plus m of x minus x naught. And we know this because it's at x naught, you'll have y naught plus m times, well, this is 0. So it's just going to be y naught, which is what we need for it to be tangent. So then we would have at x naught minus 1, it'd be y naught plus m times x naught minus 1 minus x naught, or y naught minus m, because x naught and x naught kill each other, so you're left with minus 1 times m, and this has to be equal to 0. And the defining property of the tangent line is that m is equal to f prime evaluated at x naught. Right, so that's the first step. We then want to solve this for f of x. Now what we do is slightly clever. This is step 2. We iteratively use the linear approximation. What do I mean by that? Well, we have the tangent line be a good approximation for very small h. For h much less than 1, right? So we can do it in one step, or we can say, aha, then at x naught plus 1/2 of h, we just say that's f of x1 plus 1/2 of h. Then use the linear approximation, which would be f of x1 plus f prime of x1 times 1/2 of h. But then the property defining it is that the derivative is equal to itself times 1/2 of h, which is then equal to 1, right, just by distributivity. And then we do the same thing again, since f of x1 is f x naught plus 1/2 of h. But we did this. We literally just did it. We just called x naught x1. So we have again f of x naught. So doing it in 2 steps instead of 1 gives us 1 plus 1/2 of h, all of that squared times f of x naught. And similar reasoning can do it for 3 steps. X naught plus 2/3 of h plus 1/3 of h. And I'm going to leave it to you to show that it's going to be then equal to 1 plus h over 3 cubed f of x naught. And by induction, we can keep going for any n and show that it's equal to h over n raised to the nth power f of x naught. And indeed, when we take the n to infinity limit, of this is going to be equal to, well, this limit is e to the h times f of x naught, and that's what we were looking for f of x naught plus h. But now, although the derivation used the reasoning that h was small, h doesn't need to be small, because if we go in multiple steps, we can divide it into small pieces. And this basically says, yeah, we could divide it into as small a piece as you want, and we'll still end up with a way to get an arbitrary distance h from x naught. So then we know that f of x can be written as f of 0 plus x, which we've just shown is e to the x f of 0. And we've assumed f of 0 is non-zero. So that's the general shape of the curve. It's going to be f of x is equal to whatever y at 0 is times e to the x. And that's the curve that we were looking for. So this originally was called the problems of inverse tangents, where you'd specify the tangent line and say, now give me the curve that satisfies it. But we now group this under the field of ordinary differential equations. So this was just a brief introduction to ordinary differential equations with a historic problem. So yeah.